Okay, hi everyone. Thanks for coming. You all know the spiel by now, and I'll keep this super quick, but this is the final lecture in our summer series. Thanks everyone for coming so far. So far, we've had Jose Sanchez, Hyeban Song, Trevor Scholes, Maracana, and now we have Francis Tseng, who I'll introduce. So Francis works primarily with simulation and machine learning. He is currently lead independent researcher at the Jane Family Institute, and in the past, he was a designer at IDEO, adjunct faculty at the New School, co-publisher of the New Inquiry, researcher in residence at New Inc., fellow at the New York Times, and worked on spatial economic modeling at the Institute for Applied Economic Research. His research interests include how algorithmic systems, climate change, and logistics relate to autonomy and accountability, as well as sabotage and traps as forms of rhetoric and resistance. Francis has been working with kind of a lot of the core concepts and technologies that's on his program for quite a while, so I'm super excited that he can join for us today. As always, we'll have a brief Q&A afterwards, so prepare your questions in advance, and I'll turn it over now to Francis.
Thank you. Hi, everyone. So I'm Francis. Today I will present a few projects of mine and why I think it's important to try building things even if they already exist and even if you can't build them very well. So to start, just a bit more about me. I spend most of my time writing software of different kinds, and for the past 5 years I've been doing this at the Jane Family Institute, which is a research institute here in New York, in Soho. We have a few focuses which pretty much all have to do with finance and money of some kind, as these are, of course, big bottlenecks for ambitious policy in the US and throughout the rest of the world. And many problems that people have could be boiled down to just not having enough money. So we're concerned primarily with questions of how do you get money and how do you send it to the places where it needs to be. So for example, I've worked on projects related to the energy transition and how you finance that, and I'll talk more about that in a bit. We also do work on what are called social wealth funds. So if you're familiar with the concept of a sovereign wealth fund, it's somewhat similar to that. So some polity has some common pool of wealth, which is usually related to natural resource extraction or something like that. So for example, the Alaskan Permanent Fund or Norway's Sovereign Wealth Fund and so on. But in our case, we're concerned with how those funds are used towards social programs or development or that kind of thing in particular. So more concretely, my work has consisted of producing maps like this one. So this was for a project called Mapping Student Debt. And here we visualize student debt through the US, and we try to uncover spatial patterns or patterns related to what we call school concentration, so and debt levels. So is there a relationship between the average amount of student debt someone carries and, for example, the number of schools that are in their area? So if there's any kind of effect of monopoly or concentration. Let's see what else. I also occasionally work on more public-facing tools, like this one, which was for the Public Bank of LA movement. The goal here was to help illustrate to the public and to the LA City Council the potential benefits of a public bank. So for example, it may be not super clear here, but you can kind of tweak the allocations to each of these different aspects of the bank, of how the bank uses its money, and see its impacts on improving housing access or helping finance worker-owned co-ops or producing green energy. And so this was presented to the LA City Council, and then they actually did end up approving the next step of the project, which is still very far from an actual public bank happening, but it's nice to see nonetheless. And then the last major category of software that I work on at JFI are tools that are meant for more specific esoteric uses. So this here is what I'm currently working on, called MEFRS, a tool to help countries design royalty schemes for natural resource extraction. So the context here is that with green energy technologies, we can expect to see a shift of economic importance from petroleum-rich countries to those rich in what are called critical minerals, which typically means those that are important for things like batteries, but it can also mean minerals that are important for computing, GPUs, et cetera. So naturally, if you're a poorer or less developed country, then having these kinds of natural resources is an opportunity to bring in money and develop. Typically, it would be a foreign corporation that comes in and does the actual mining and processing because they have the capital, the expertise, the technology, et cetera, to do so. But as a host country, you don't want to be cheated out of this natural wealth. You don't want to get screwed over in a bad deal. So you want to allow access to these resources on favorable terms and ideally in a way that minimizes social and environmental impacts. So for example, you might include a tax to, I actually don't know if you can see it here, but you might include a tax to fund decommissioning at the end of the mine's life so that the company just can't leave and stick you with the bill. And one of the reasons that we built this tool is not only to kind of explore the different impacts of different tax designs around this, but also because there's many sources of uncertainty. The most evident here is in market price volatility. So if you're mining lithium, for example, you have no guarantee on what the price of lithium will be in the future. So that could have a big impact on the actual royalties that you obtain as the host country. So you want to, and there's also things like currency risk too, like maybe, I mean, the US dollar has kind of been going up and down lately. And if you're a country where those swings are wider, that can also impact the royalties you obtain. So you want to ensure that your royalty scheme is at least somewhat robust against these scenarios. So this is what we're working on now, and I think this will actually be made public too, if I'm not mistaken. So when I was putting this presentation together, I wanted to come up with some through line for all of the work I'm presenting, and I stumbled on overdoing it yourself, because basically I spend a lot of time writing tools, and it's often kind of redundant or kind of a waste of time, but hopefully I can make that make sense. So here's some tools that I've worked on just to give some categories of things that I do. So this here's a tool called Dust. This represents a category of tools which are a lot more specialized. This one here in particular is just for generating chord progressions that you can then feed into music software synthesizer or something like that. And for me, this represents tools for which there aren't really usually an alternative, so you end up having to roll your own, but that's not always the case. So here's another one. Then there are things like this on-screen keyboard for like a tablet. There are plenty of on-screen keyboards that already exist. They just didn't have the feature set that I wanted. In this case, I wanted to be able to specify the layout myself, define special keys, and so on. So in this case, there are these tools that already exist, but lack something that I feel is crucial, so you write your own. And then there are tools that 100% have many, many well-written and battle-tested alternatives, and this is kind of where it is really a waste of time to write your own thing. But I often just want to try writing a piece of software myself because I'm curious and I naively think they'd be simple. So this here is an image viewer I wrote. All it does is display images. It's really, really simple, but I learned quite a lot doing it. And yeah, and then there's stuff that's like a lot more extreme. So now stepping outside of software, this is a case I designed to essentially have a custom laptop. And this is where I would say I'm approaching folly, because you'll never get the same build quality or weight or et cetera as an industrial design and manufactured laptop. But it was still a really interesting challenge and a lot of fun to build. And if you're interested, there's a whole community of people who do this called the CyberDeck community. I think from Neil Stephenson's Snow Crash. And I created this presentation with a custom built tool too, so I'm doing this a lot. So now with the open source community, there are many, many people building tools all the time, and there's usually something pre-made out there that's free, and they've been made by experts and have the benefits of years of use and testing and refinement, so it may seem wasteful to write something yourself instead. And there's a lot of software jargon to this effect, especially in corporate contexts. For example, we talk about reinventing the wheel, or we use terms like not invented here syndrome to kind of jokingly pathologize this impulse. And it makes sense in a corporate context where you don't want to waste programmer hours or add additional maintenance responsibility, et cetera. But it's not necessarily a bad thing if you have some free time and are curious. And this is kind of, yeah, a trope within the Linux community in particular, people writing things over and over again. And even though it can take a lot of time and effort, there are a lot of benefits. So for example, in cooking, there are many, many different kinds of knives. You have a general purpose knife, which in Western cuisine is a Western chef's knife, and in Chinese cuisine, this is usually a cleaver of some kind. And they can do most jobs fine. If you're doing something more specialized, like cutting bread, it'll do fine as well, but only if it's something you do infrequently. But if you're gonna be doing it a lot, you probably want a knife designed expressly for that purpose, like a bread knife. Then there are uses where you could use a chef's knife, but it's not advised, like chopping ribs, as you could hurt yourself and damage the knife. I don't know if any of you ever tried that, but you can chip the knife and it can glance, and it's pretty bad. I would say the same is true for any other software tool. If you're making pixel art, you could do so with Photoshop. It's possible, but probably clumsy, and at points may feel like the software is working against you. Or you could use a tool specifically designed for that, and it would be much more ergonomic. Similarly, when you write your own tools, you can design it to function according to your own mental model of the task, and you don't have to learn somebody else's. I find this is often why I'd end up doing this. Like having a very specific control scheme that feels a lot more intuitive to how I think. And you avoid this kind of jack of all trades, master of none problem as well. Okay. So to give some more examples, for several years I've been working on a game called Fugue, inspired in part by Buddhist mythology, the 60s and 70s period of revolutionary violence in the US, things like the Weather Underground and the Black Liberation Army and the Symbionese Liberation Army, which is a very interesting period of US history that I think is often forgotten, the Paris Commune, and many other things. And then, yeah, making a game is a lot of work, obviously, requiring the production of many different assets like characters, environments, dialogue, etc. And so to facilitate that, I've written many tools. And in fact, I've been working on this probably for like 5 years now, and in fact, aside from writing and world building, I've probably spent the majority of time just writing tools for this game. So I don't actually have that much to show for it just yet, but we're getting there. For example, for the script and dialogue system, so I wanted to have like a very kind of complex branching dialogue system where there's a lot of player agency, and that can get quite complex. So I wrote an editor that aims to make writing that kind of nonlinear dialogue feel a bit more closer to writing something in Word, where you don't have to really think too much about how everything fits together. So it includes like different features to help ensure that I'm not writing contradictory branches or that I don't have any dead ends and so on. So that tool is on the left here, and then this is what the syntax for writing a script looks like, and this is just an example of me testing the script, the dialogue system. And then one particularly important and normally time-consuming task is creating character models. So I have a character assembly system called Clay. So normally if you wanted to create a character, you'd like open up Blender and you'd do the modeling and then texture and so on, and it can take a long, long time. Instead I built a tool around this plugin called Make Human, but customize it a lot for a particular style and aesthetic. And so you can just easily just click a button and make as many characters as you want with this system. You don't have to open Blender at all. And I designed it so that you get the character as well, but you can kind of change their dress and clothing very easily. So it feels very fluid to experiment with different looks and that kind of thing. So some of you may already be familiar with this, but in 3D modeling and graphics, you'll have the model itself, the geometry, the mesh, and then you'll have a texture that's applied on top, and that's what actually gives it, the color and the texture, I suppose. And in this system's case, we have, I guess, two primary types of textures. We have the skin and like the underwear texture, but then once you put clothes on someone, actually it's probably not very visible here, but each element of clothing has its own texture. So if you have a pair of shoes or something like that, it's got its own texture. So for game optimization, you generally want to avoid having too much textures because it's extra work for the GPU. So there's a practice called texture atlasing or texture packing, where you try to combine different textures of different elements into a single texture. So you can kind of see an example here. So this is me just cutting out different textures. saving it. And then at the end here, I'm getting different clipped images, and then I'm manually, arranging them so that they tightly fit into as small as area as possible. So you can do that manually, but it's really, really time consuming. So here basically I have this is these are the clove outlines, and then I want to get something like this in the end. So I figured, okay, well, how hard could it be just to arrange shapes into a space? Turns out it's really, really hard. It's called bin packing. It's one of those things where there's no optimal solution. There's all sorts of trade-offs. There's a lot of different problem-dependent variables that mean that one algorithm is never strictly better than all the rest. And it has applications in a wide variety of domains. So here I'm just talking about arranging pixels on a screen, but it's also used in shipping and logistics, for instance, when you want to be space efficient, how you pack things into shipping containers or into boxes like Amazon boxes or whatever. Sometimes they'll use a huge box for a small item or whatever. So those are the kind of things that these algorithms help avoid. So basically I was like, okay, this is really, really hard. I can't do this myself. So I ended up using a library that someone else wrote. But I learned a lot in the process, and I have a much better appreciation of how something apparently straightforward can actually be quite complicated and counterintuitive. To the point of counterintuitive, this is like a joke that it circled the internet, I guess maybe a couple years ago or something, where this is apparently the most efficient way to pack 17 squares into a larger square, and it just looks completely made up. It's like a shit post or something, but that's apparently the actual solution, at least at the time. There may be better ones, but they all just look really wrong to us, I think. So it's in terms of writing your own tools and failing at it, this is something that this humbling aspect is what I like the most. Things are usually more complicated than you think. Sometimes things feel like magic and it's too easy to take them for granted. In general, I believe it's very important to understand and appreciate how the things we use or experience in our quotidian come to be, and being naive and trying to do things yourself and failing in the process, I think is a good way to learn that and to do that. So the same kind of dynamic of trying to do something, thinking it's simpler than it is, and then failing and then learning a lot about it happens in my simulation work at JFI. Although there I typically have more humility at the outset because we're usually working in domains for which I have no expertise. I'm usually working with other experts to inform the model's design. So for example, this here was my last project before this mining one, called Impulse. And the basic idea of the project was we were talking with the Loan Programs Office at the Department of Energy, and their mandate is basically to give money out to new green energy projects and try and accelerate the green transition in some way. So this is kind of this problem where you have these new technologies that seem promising, but they're very, very risky because only a small fraction of them will ever actually reach market viability. So no private investor wants to invest in something so risky. So usually the state comes in and provides some gap financing to hopefully get these things to the point where they have more market viability. And then at that point, private investment steps in, and that's when you see big growth, because now they're like, okay, I'm less scared of this, and I'm happy to build new power plants using this technology or whatever. So we wanted to basically figure out if the Loan Programs Office could be more strategic in how they gave this money out. As I understand it, they were kind of looking at a project-by-project basis, but in theory, developing a better hydrogen electrolyzer or something like that might help other projects in their portfolio also benefit from these kind of spillover effects. So this was a model basically for that. We have all these different sources of energy, different energy technologies. We model private investor behavior, and we try to figure out how can we strategically allocate this public funding so that we can bring down the cost of green energy at a faster rate than we would see otherwise. And here are some of the questions that we use to guide the model's design and development. And the Loan Programs Office, the term they use is catalytic investment, I think, because it's basically like this step function, I guess, where they put enough money in, and then you have, I mean, solar is kind of always the example people use, but solar used to be very, very expensive, and then over the past 20 years or 30 years, the prices dropped drastically, and so they're hoping to kind of figure out how much investment they need to get, let's say, like batteries to that same level, that same cost reduction. So there's a lot of failing in the simulation development as well. As you can probably guess, debugging these kinds of simulations can be very, very difficult because you have a lot of interacting components and moving parts, and you'll see weird interactions that lead to unexpected behaviors, occasionally revealing something that you hadn't considered. For example, the model kept showing that natural gas would continue to remain relatively dominant into the future, and I think we were expecting otherwise. We were expecting that eventually wind and solar would start to take up more of the majority. But the problem with a result like that in these kinds of simulations is that it's not immediately clear if something's actually wrong with the model or not. You don't know if we implemented something incorrectly or if this is actually just what we should be expecting. So another example here is that investors just eventually just stopped investing in new power plants and new power capacity because the margins were so bad, and then eventually the whole electrical system collapsed because there's no new capacity being built. So again, the first question is this the correct behavior? Like under our assumptions and the conditions we specified, is this actually the logical result or not? Or did we accidentally misconvert a value or misspecify a unit or something like that? And then if we can't find anything obviously wrong in our implementation, then are we not representing something in the model that prevents this from happening in the real world? Because obviously, so far at least, we've had enough capacity for growing energy demand. So something's missing in the model, and then in this particular case, we kind of started getting into this messy world of electricity markets and utility rates and subsidies and just like all this policy machinery that's in place to kind of prevent these kinds of outcomes. The other thing I want to mention here is that one thing that makes these models difficult is that there's a lot less hand waving that you can do, which isn't to say that there isn't any, it's just a lot harder to get away with. You generally need concrete numbers, and it's really hard sometimes. It's easy to say that you have a vibe about how something works. It's another to actually put numbers to it. So for example, a very, very simple and fundamental question here was how much capital is available for energy projects in general? Like, is it how many millions or hundreds of millions or billions is it, or trillions? There's not like a number that you can just Google and find. I mean, there are sometimes estimates, but they may be estimates for specific countries or very specific technologies and so on, and we needed something more general. So something even as simple as that is quite difficult. Similarly, how are electricity prices determined? That's very important if we need to compute the financials of a particular energy project. And that's also very, very hard to come up with. It's easy to just be like, oh yeah, the market and supply and demand and whatever. But then when you actually have to concretely write out, what level of supply, what level of demand, et cetera, results in what particular price, it's really, really hard. Okay, so moving on, in 2022, we released this game called Half-Earth Socialism, the game, which I worked on and helped design. So this is also a kind of simulation that's not too dissimilar from Impulse, which I just showed. But obviously, being a game, it has somewhat different priorities. So this game, accompanied this book, Half-Earth Socialism by Troy Vitesse and Drew Pendergrass, that came out at the same time as the book. And I don't know if any of you have read this book or not. Oh, you've all read? Okay, cool, okay. So that's awesome. So you may remember then part of their vision is this idea of this participatory planning. And I think they have if I remember correctly, they have a little bit of fiction either at the beginning or the end, and they may mention what that system might look like or not. But this game was in part conceived to kind of be this AirSAT's participatory planning simulator or tool. So in the book, the idea is that people democratically participate in decisions about, like, do we invest in nuclear energy, or do we try to go all wind and battery or something like that? And so you need some way to communicate, the trade-offs, downsides of these decisions, their costs, and so on. And the book was, a lot of the book in this regard was inspired by the work of Otto Neurath and his isotype, which is basically his proposal, his idea. So he's like, well, how do people who are working and stuff, they don't really have a lot of free time. They're not going to be educated in all these different topics in the same way that someone who can actually devote, their full life to studying these topics can be. So how do you communicate enough of this information that they can make an informed decision if they're going to be participating in this democratic planning? And so his idea was these kind of pictographs, these infographics, as being a way of doing that. And so I think our game here is we kind of conceived it as the next step for that, where if it's hard to represent, the dynamics of a moving system through a static visualization, but a game might be a good way to do that. And it was the effort of a lot of people. I think the game's been translated into 7 languages now, which has been amazing. These are all volunteer translators too, which has been super cool. But to just briefly summarize how the game works is that basically you're like a lead planner in this world, and I think we started in, I guess 2022, was it? Yeah, I guess it must have been. And you help decide what projects the world pursues in order to achieve its goals of lowering greenhouse gas emissions and biodiversity loss, and ensuring a good quality of life for everybody. And so you make decisions about how much of our energy should be produced with solar or wind power, or if you want, you can stick to petroleum and natural gas and so on. And so under the hood of this is a simulation that basically says, like, okay, if this much of the world's power is being met through this method, how many emissions are producing, what's the pressure on biodiversity, how much land is being used, how much water, et cetera. And there are a lot of also these weird kind of counterintuitive results that at first I thought were maybe bugs or something misimplemented. So for example, in the game we have 2 types of hydrogen, which are fuel replacements. So we have blue hydrogen, which is produced from natural gas. Actually, no. What was it? We have gray hydrogen, which is produced from natural gas. Blue hydrogen, which is, I'm getting blue and gray confused. One is from carbon capture, and one is from natural gas. And you have green hydrogen, which is produced through electrolysis using ideally renewable electricity. And basically, I think when I was playing the game, I was like, okay, you generally want to go for green hydrogen because you need a fuel substitute, and that's the cleanest one. But then when we did that, you just always lose the game because it would end up just skyrocketing your energy usage. And I thought something must be wrong. But it turns out that that's just the case. Like right now, electrolysis technology is really, really energy efficient. So it's actually kind of unviable. And then something similar happened with vertical farms. I think people, especially people who aren't super, don't follow agriculture that much or whatever, vertical farm seems kind of like intuitively like a good thing that we should be pursuing because it has a very low footprint. On paper it has lower water usage and so on. But it's actually quite inefficient compared to just like regular terrestrial farming. And it was really difficult to find actual numbers about like water and energy consumption per calorie produced. I think all we could find were things about like strawberries and maybe arugula or something like that. So we had to do our best to extrapolate from that. But it's just, again, like really high energy usage and doesn't totally make sense. So it was interesting. It challenged a lot of things that I thought I understood about all that in the process. So these are just more things you can choose from. The game also has a lot of these different events too, to represent things that weren't so easily captured directly in the simulation. So like we couldn't model specific species, populations, or things like that, but we were kind of able to graph those on through these events. And then the other thing is that we wanted to make sure, I think this was the primary challenge in designing the game, was figuring out how to not make it have this God view. So if you play any of these other kind of like SimCity games or something like that, you're kind of unilaterally making all the decisions. And we struggled for a while trying to figure out a design in which felt more like you were participating in a democratic process. I don't think we really managed to get there in the end, but this was kind of the closest we could figure out, where you have a government parliament, you have different interests represented, and you kind of have to balance their interests and needs and desires in order to keep playing. Well, this is kind of small. One of the neatest things that come out of the game was we released it on Steam. I don't know if any of you have spent much time in Steam forums, but they can be, I don't know, they can just be like kind of difficult, I guess. And we saw a lot of really interesting conversations. Like I think one of the main threads that ended up getting really long was people just debating the merits of nuclear energy technology. That was super cool to see. We had some more benign kind of commentary like this. So this person's upset that they feel like the game is forcing you to pursue a very particular path, but that's not really us. That's more a consequence of the model itself, unless that's something we explicitly designed to like be the only way you could win. So I thought that was interesting. And then you have people accusing us of like, what was it? Someone was like, is there a way to make people starve or something like that? Because that's what would actually happen. So you have kind of more deranged commentary as well. And then a couple years after the game's release, we also released an editor that lets people configure the world parameters for themselves. So a lot of people, for example, with nuclear especially, disagreed with how we represented its emission profile, its like risk level, et cetera. And so we always wanted to make it so that if you felt like, if you disagreed with the parameters that we used, you're welcome to kind of create your own world in which the parameters are close to what you think are true, and you can share that with people, and then you can play one in that one instead. I think part of it's this idea, again, of like giving people space to try things and then fail, or figure out something better than how we did it, because especially in the intervening years, there's maybe better data to use to actually specify these parameters. There's a lot of different types of nuclear power technologies that we didn't really represent individually back then, like small modular reactors, like I guess thorium and that kind of thing. So there's always room to kind of continue to develop and refine this, and so that's what we're hoping our players do. I think that's it, actually. Yeah, that's all I have. So yeah, thank you.
Great. Thanks, Francis. Does anyone have a question kind of right away? If not, I'll let you go first. No, you should, please.
Okay. Hi. So yeah, as I mentioned, everyone in the class did read at least some of Half-Earth Socialism. We looked at a few kind of like Let's Play videos. I was curious about the process of like working, I don't know my question is like to know a little bit more about the process of making that game. For instance, you've got the book, it's kind of coming out of like social sciences maybe, or maybe a bit of philosophy and public policy or something. So you've kind of got that material, and how closely were you working with the authors of the book? And then to what extent were you like drawing on established game design, like document techniques and theory about how games should be built and how you create this yeah, I was just curious, like, because in a way it's like a transmedia project, right? Where the project kind of crosses very successfully between two entirely different mediums.
Yeah, we worked very closely with the authors of the book. The way the project came about was that Verso, the publisher, they originally wanted a friend of mine to make a website as part of the book's marketing, and then he counter-proposed, well, let's make a game. And so that's kind of how the project came to be. And yeah, the whole process, we worked very closely with the authors, because Drew in particular, he plays video games, and he also works on, he's a atmospheric chemist, so he's fairly familiar with like he's very familiar with like, various climate models and that kind of thing. So he kind of brought that aspect too. And in fact, the game itself uses like a real climate model called Hector, which I think he was the one who introduced us to. And it uses that to compute the temperature anomaly based off the emissions of the years in the game. But then in terms of how we designed the game, we had this period where someone else worked on the game, Kiara. We had like a little reading group. And so we read a lot of stuff from like a lot of different sources. A lot of the authors were inspired by Soviet cybernetics. And so we read on some of that and this idea of like algorithmic planning and that kind of thing. I don't think I showed it here, but you have this little character that kind of guides you through the game called Gosplant. And that was kind of inspired from reading from that. And then we played a bunch of games too. We played Frostpunk, which is this game, this like top-down strategy game in which the world is plunged into this new ice age, and you have to like manage the city. And it's very interesting because the whole game's design is around heat and how heat radiates. And so we were trying to think, like, obviously heat is an important part of this game, but not quite in the same way, but we were kind of looking for, I think, analogs there. We played this mobile game called Reigns from, I don't know, like 10 years ago now or something, where it's kind of like has this Tinder-like interface where you like make story decisions by swiping left or right. And we liked that because it was really, a really simple interaction, but it was very effective in actually like kind of unrolling out the story. So that's kind of where we got the scanning card mechanic, I think, was originally inspired partly by that. And then we looked at a lot of these like serious games. So there's this one, I forget what it's called now, but it may have been like funded by the UN or something like that, where you're like managing the world, and it's like really complicated, and there's like all these tables. And it was a really interesting game, but I think it was just like so numerically dense, so we wanted to avoid that as well. So we just like read and played a lot of things.
Francis this before, but the writers of Half for Socialism were in the AD lecture series like 2 years ago, and they talked for quite a while about the game. Also, because I think that was probably what they were assuming, that like the audience of architecture students would interface with the most, given that it's like, I don't know, the designed part and where it like comes into action. But I have one question, and then whoever has another question, just raise your hand. I'll grab you a mic. But Jose. A bit of a two-parter, just on simulations. So I would imagine either at JFI or in Half for Socialism, when you want to understand, I don't know, how investment relates to kind of energy plant production or something like that, you might find sort of open source economic models that are out there. So just one, like, is that the case for various things? And then two, in the case that there are existing models, kind of what is the conversation or thought process behind, should we just use these as we are? Should we open them up and, kind of revise them? Should we make our own, et cetera?
Yeah, that's a great question. So in terms of there being other like models, open source models, there are. So for like Impulse in particular, the Energy Finance Project, the National Renewable Energy Laboratory, NREL, they have a lot of models that are free and open source, and they're kind of the experts on this. They have this one that we refer to a lot and that we actually use the data from, called the Annual Technology Baseline. And they kind of have these different categories of different energy production technologies, and they have different cost profiles and all this other stuff. And so they have like huge teams of people that produce all those numbers. So there's that, and then I want to say there's probably some other ones that I'm from other research institutes, but I'm blanking on them. And so yeah, it's common like, why don't we just use that one? I think so. One reason actually is that there is, so for example, in like climate modeling in the, I'm forgetting the name. It's not GIEC, it's the IGCC climate reports. they never just use a single model. They usually take the output of many different models. And it's because that, a single model is probably going to have some kind of systemic error in its output, where like maybe, one assumption they did or one way they implemented a particular system might lead to slightly biased numbers coming out on one side. And so the idea is it's like in machine learning, you also have this concept of ensemble learning, where you train several different models, and they're all slightly wrong in different ways, but together their wrongnesses all kind of average out, and so you get an overall better estimate. So that's one reason why like a lot of institutes will build different models that do the same thing, is so that we can all have our little errors kind of cancel each other out in the end.
Thanks again for the talk. I was very curious about the tools that you built for your projects with the Fugue game, I think that you mentioned. There's a series of tools, and my first question had to do with like, do you usually produce those tools for yourself, or do you kind of open them up in some way, and also, what is your reflection on some of these tools being able to facilitate collaboration? Because my experience with larger projects is that one of the big challenges is really kind of syncing data across different people. Of course, we have like Git merging kind of repositories, but at the same time, it seems like some of these tools suggest like a cloud infrastructure that could kind of plug itself, like that multiple people could change or edit simultaneously, and then ultimately like deliver kind of a final product. I was wondering if that's the case, or your thoughts on that.
So for a lot of the smaller tools that I write for myself, I mean, I publish everything on GitHub, but I think it doesn't really mean that much, because I don't know, you have to like look on my GitHub to find things. So they're all available. Sometimes there's some tools that are actually just modifications to existing projects, and so those changes usually will get merged in or something like that to the actual project. But then in terms of like collaboration, so actually, I don't know if this still, let me just see if this still works. For Half Earth, we had an editor, editor.half-earth. If it's still up, I can show it. Oh, no, I guess it's just the new one now. How do I exit from this? So this is actually the new one, but we had an older one that we used for the actual development of the game. And it was just like a synchronized thing, so we could all just simultaneously edit things. So we had like Troy and Drew entering values that they knew. We had some people helping us with research and fact checking, and they could just edit the things here and they would all be synced. And then when I wanted to update the game with the values, I would just download this one file, and that would be it. So that's probably the most recent example. So yeah, sometimes we'll write things specifically to facilitate collaboration in this way.
Sorry, just to follow up briefly on that. And it seems like a similar infrastructure is thought to be a modding tool, like later for the public, right?
Yeah, exactly. So that's basically what this turned into. And that was an idea we had at the beginning, because Arthur, who was one of the people who worked on the project, he was a really strong advocate of that. And so it kind of worked out that our editor could easily be turned into like a modding thing,
When you talk about climate modeling, is this like using ML models?
It depends. I don't know how common that is. It's probably become more common. Something that I don't really have that much of an intimate knowledge of. But usually they're just physics-based. They're like written in Fortran to be like really fast. I think it's often just equations, but for something like Hector, which was the climate model we used, I think you'd be more like, Hector doesn't do this, but I think you'd be more likely to see machine learning in there because it's computationally cheaper at the cost of being accurate.
Yeah, I mean, you kind of already spoke about this, but I'm interested in like how you measure the accuracy of a model when there's no baseline? Like in ML, people use like a lot of metrics like recall, and you have like your training data. But yeah, if you could speak more on like whether you know whether it's sensical or not.
That's a great question. That's the kind of thing that I think is for me at least, like the biggest challenge, because there's often not like a data set that you can, compare to as you can with other machine learning models. Sometimes what you do is you just compare to the output of people who have made similar models and just hope that there's some kind of rough consensus among there. But obviously that's not great, because if everyone's wrong, then it doesn't really help. Sometimes one thing you can do is what's called like back testing. So, if our energy investment model, like we're starting from 2025 and projecting out to 2050, what we might do is actually go back 20 years. And then if we have data up to 2025, we just see if we reproduce that. But yeah, it's challenging. There's often no ground truth that you can really, anchor your confidence to in terms of the model being working correctly.
Okay. Well, thanks, Francis.
Yeah.